Good morning, everyone. So, welcome back to the penultimate day of this meeting on special holonomy and geometric structures on complex manifolds. And I'm very pleased to introduce our first speaker today, who is Simon Salamon from King's College, who's going to tell us about weak holonomy with symmetry.
Thank you, Jason, and a huge vote of thanks to the organisers. I think it's turning out to be a very enjoyable week, productive week also for me, and very lucky to have an invitation to come here, and it's an invitation I really couldn't refuse. So thank you very much. I'm going to talk about sort of a jumble of things which I hope to sort of link all together. Well, first of all, the picture, I think, is the picture from Claude's hotel room. I'm not lucky enough to have such a view. Anyway, this has grown out of work with Ragini, my former postdoc, who's currently in Brussels. But I've also been talking about some of the things with Fabio Podestà in Florence, and a PhD student. LSGNT is our London PhD training centre. So Elva Atlason is doing a project with me, and talking with him has helped me sort of clarify a few things. So the plan, oh yes, and I'm also, part of the talk is based on my understanding really of links between the Hitchin orbifolds, which we've already heard about, I think, and positive curvature, which is work of Vizilla and collaborators. So I make no apologies that part of the talk will be explaining my understanding of that. So as I say, in a sense, this talk grew out of my attempt to understand a bit more about the metric, the homogeneous metric on Berger's space, 7-manifold SO5 over principal SO3. And that was essentially, I think, I'm saying in Robert's paper, that was essentially the first example. It's a so-called nearly parallel G2 manifold, and it was the first example that enabled one to write down a metric with exceptional holonomy, because its cone, we now know, because it's nearly parallel, and I'll explain that concept later, its cone has holonomy spin 7. So that's sort of very dear to my heart, that manifold. But I'm trying to understand a bit more about its metric, all being a homogeneous metric, led me to these other topics, which I hope to cover during this talk. So normally in these talks, I have all the references at the end, and I never finish the talk, so no one sees the references. So I'm not going to dwell on this, but this is the last slide. So if I don't get there, you can, I'm sure, look at the slides afterwards and find the relevant references. And I won't be citing all these, but the work sort of developed, I think, from about 1995, which was also the time that Dominic Joyce found compact examples with exceptional holonomy, although I'm not talking about that today, so I haven't cited him. So I want to start with what I regard as a bit of a trick, which is to do with moment maps and co-adjoint orbits. But first of all, there's a word for one of our sponsors, just to remind you that if you have a holonomy group, in the cases we're interested in, it acts transitively on the unit sphere. But I know that this conference is also about complex manifolds and structures on complex manifolds. So I want to really start with adjoint orbits in a compact Lie group. So I'm going to choose an adjoint orbit, which we know is necessarily, so that means an orbit of the group acting on its Lie algebra. We know that that will necessarily have a sort of symplectic and indeed a Kähler structure. So I'm starting with a Kähler manifold, but typically it will be either CPN, projective space, or the quadric in these slides. And I'm just going to project that. Well, first of all, you can think of that as an orbit, so it's embedded in the Lie algebra, in the vector space consisting of the Lie algebra, but then you can project it to sort of subspaces of the Lie algebra. And the initial examples I'll be projecting simply to, I'll be choosing a subalgebra H, of G, and I'll be projecting to the complement, or if you like, the orthogonal complement or the quotient of H in G. And then in other examples, it will become a bit more complicated. I mean, when things homogeneous, and I'm interested in the case actually in which H acts with cohomogeneity, essentially 1 or 2, but the first examples will have 0, which of course is elementary from certain points of view because the maps are homogeneous. So that's what I'll be doing, and I have about 4 examples of this setup, which I'm sure you already know about, but the way of presenting them is maybe slightly new, I hope. So as I say, I'll just be doing very simple examples in which the complex manifold will either be complex projective space, CP3, CP2, and towards the end I want to talk about complex quadrics. Q5 comes up in Robert Brandt's work concerning holomorphic curves in S6, for example. And the reason this is meant to be a solid tetrahedron, sort of 3-simplex, and the reason I put that there is that had I instead chose to take the adjoint orbit and then choose a maximal torus, take H to be a maximal torus, and just project to the Lie algebra of the maximal torus, so that's actually inside G, we know that the image is a convex polytope, and for CP3, the image is, of course, just the solid tetrahedron. Okay, and actually, this picture is taken from a talk I gave about more than 20 years ago when I was trying to classify almost emission structures on the Iwasawa manifold, invariant structures on the Iwasawa manifold, which is mentioned in one of the posters. It's a 6 manifold. I'd fixed a metric, standard metric, so because everything is sort of invariant, it's really just algebra. So you're interested in almost emission structures, so you're reducing the orthogonal group to U3. So any invariant almost emission structure is an element of that homogeneous space, but this happens to be CP3. And somehow we'd sort of parameterize these things. Unbeknown to us, there's a sort of toric symmetry, not obvious, but it therefore turns out that the classification of these different types of almost emission structures like complex, symplectic, blah, 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 are points of this solid tetrahedron. And I was actually using the moment map. I didn't realize it, but I was using a tetrahedron, which was just the image of the moment map when you project to the moment map for the maximal torus. So it's just toric geometry. And I mention this because often you use moment maps without knowing that you're using them because it's so natural. Okay, so here's my first example of the previous setup in which the group G is just the quaternionic unitary group SP2, which is a subgroup of SU4, which is roughly the usual isometry group of CP3. So see, all these spaces, these adjoint orbits are always G over C, where C is the centralizer of a torus. Here it's roughly U3. So I can therefore take my CP3, think of it as embedded in SU4 by the usual moment map for its symplectic structure or Kähler structure, and then project to M. But M here is really just R5. But if I think in terms of complex representations, it's the primitive 2 forms on C4, which has C4 is really 2-dimensional quaternionic space, so there's a real structure. So this complicated looking thing is really just R5. So you're just projecting CP3 to R5. You can normalize everything, take a vector in Z4 with unit norm, and it's pretty clear that the map, because this is just homogeneous in this case, just has to be roughly Z wedged with J of Z. Okay, so that is the map to R5, and that will define the usual projection from CP3 to S4. Okay, I won't dwell on this, but you can make this very explicit, if you haven't seen this before, by just writing Z, a vector in C4, in coordinates, homogeneous coordinates, well, coordinates, homogeneous coordinates for CP3, and then you know that J of Z, we have this sort of it's real structure, but it's really multiplication by the quaternion J. This is in the usual way, minus Z1 bar, Z0 bar, minus Z3 bar, Z2 bar. Thinking of this as H plus H. And then you can just do the wedging and quite easily find the formula for mapping CP3 to S4, which you'll recognize, you sort of get the inverse twice of stereographic projection. You get a familiar formula, but it avoids having to sort of directly use the quaternionic projective line and a couple of quaternions. So that's just an example of the sort of moment map I'm talking about, in which you project to the complement, you take the full moment map and just project to some subspace of the Lie algebra. And again, because I'm interested in complex, of course, the disadvantage of this map, it's been used for many purposes. In a sense, it's just the Hopf map. But developed by Penrose to sort of relate the real geometry, real Riemannian geometry to complex geometry in many different ways. But of course, CP3 doesn't have the same dimension as S4. It'd be quite nice to have a complex manifold of the same dimension as the sphere, and that's what we'll be looking at other examples later on in which that happens. So I'm more interested in examples in which the complex manifold here has the same dimension as the base manifold. But of course, you can easily achieve that, if you forget homogeneity, by just choosing some algebraic surface in CP3. The most obvious one is just a plane. And what happens, well known, that would just project it will be one-to-one to S4 apart from at a point. So we're really saying that CP3 is like S4 blown up in a real sense at one point. That's not terribly interesting. More interesting is to take a quadric, particularly a J-invariant quadric in CP3, and that will define the sort of standard complex structure on S4 minus S1. It will be 2-to-1 away from a circle. S4 minus S1 can be thought of as just the product of these two Riemann surfaces, S2 and the upper half plane, and the complex structure is just the product complex structure, but this is sort of Kähler conformally flat. And
So when you say there's a real quadric, it's a complex quadric, which is invariant under J.
It's a complex quadric. Yes, sorry, it's a complex quadric, which is J invariant, yes. So it's real 4 dimension, same dimension as S4. And the reason I've written this in red is that I'll be mentioning right at the end, if I get there, you will see this quadric cropping up again, such quadrics in CP3 cropping up again. Okay, that's just an example, but it's sort of setting the scene. Now, there's a completely analogous, try and remember this formula here sorry, it's too soon. This formula here my formula here for the Penrose mapping. So I'm taking a vector in CP3, in C4, and I'm just mapping that to Z wedge Z, JZ. But think of J, think of the action of J as like conjugate. It's some sort of real structure because J squared is, well, on CP3, it's the identity. And then you see you can do exactly the same thing. It's another well-known example of this phenomenon. You can go down now to CP2 and do the same sort of trick. So I'm thinking of CP2, of course, the isometry group is SU3 over, sort of CP2 is roughly SU3 over U2. I don't care about U2. But I want to choose a subgroup of SU3. Well, of course, you have SO3, the real matrices inside SU3. So when you apply the trick, you're first of all mapping CP2 into the Lie algebra of SU3, but then you're projecting to the complement, which is again R5. But instead of being lambda2 something, it's S2 something. So it's really completely analogous. And the projection this time is clearly going to map a vector in C4, or in the sphere, if you like. Instead of Z wedge Z tilde, it's Z symmetric product Z bar. Now the real structure is ordinary complex conjugation. And again, you have to take the primitive thing because R5 is the set of sort of trace-free symmetric matrices. So that's the formula, completely analogous to the previous slide, but this time it defines, it's not, of course, we're now in the cohomogeneity 1 situation, and it defines a 2-to-1 covering, branched covering from CP2, well known, to S4. It's all invariant by SO3. And clearly what's going to go wrong here is that if Z happens to equal Z bar, and that occurs on an RP2, then the thing will be 1-to-1. So you get this branched covering of CP2 over S4. Okay, now that's a well-known example. But of course, that leads you to understand that SO4 is also acting with cohomogeneity 1 on S4. The generic orbit is SO3 over the Klein 4 group. And there are 2 singular orbits, which are both RP2s, Veronese surfaces. And if you want to relate that to the map I've just defined, then the inverse image by rho, you see we've only got one sort of bad set in CP2, namely RP2. We've got 2 bad sets, 2 singular orbits, where the SO3 orbit is 2-dimensional rather than 3-dimensional. They're both RP2s, but the inverse image of one of them is the RP2, where the mapping is 1-to-1. The inverse image of the other is just the conic in CP2. Okay, so perhaps I said something slightly wrong. I mean, there are 2 singular orbits in CP2. One is RP2 and one is a conic. Well,
A conic, right.
yeah, conic, well known. Yeah. Q1 is a conic. Okay, but the other thing this tells you is that S4, if you think of it as with its orbifold structure, you can just, I mean, complex conjugation, of course, preserves the Fabini-Studi metric, well known to people in quantum theory that the isometry group of Fabini-Studi metric is the sort of holomorphic isometries plus complex conjugation. So that actually gives you S4 with an orbifold structure in which the metric is essentially for the Fabini-Studi metric, so not constant curvature. So this will be the first example in the famous sort of Hitchin sequence. Okay, any questions? One sort of introduction. So now, since we now know that, we've got this nice action of SO3 on S4, it's not homogeneous, cohomogeneity 1, let's study this a bit more carefully. So this comes about by, I'm thinking about the round metric on S4. So it comes about by thinking of S4 as in R5, but we're taking the action, the irreducible action of SO3 on R5, given by this Lie algebra quotient, if you like, or traceless symmetric 3x3 matrices. Now, when you're talking about metrics invariant by SO3 on a 4-manifold, you can use the basis of the Lie algebra, and you can write down these metrics in terms of left invariant 1 forms. But there's something extra going on here, which happens often in these cohomogeneity 1 situations. You have a sort of Weil group that gives you extra symmetry. So for that reason, I'm going to introduce this terminology, this trig terminology. We let alpha be 2 pi over 3, and I'm going to consider just simple trig functions, sine t and cos t, but that will be S1 will be sine t. S2 will be sine t plus 2 pi over 3, and sine 2 will be S3 will be sine t minus 2 pi over 3, if you like. And similarly, later on, I'll be using the same for cos. If you do that, it's well known that the round metric, constant curvature metric on S4 can be written in this very neat form, in which you have on each orbit, the metric has this sort of, you see this Z3 symmetry. Sorry, back. You see this Z3 symmetry, so you just have the, on the SO3 orbits, you just have the, I mean, obviously you have the one form squared, and the coefficients are just given by these trig functions with sign that I've just defined. And then, of course, you've got the parameter t, which parameterizes the orbits. And there are lots of identities that come out of these trig functions, essentially because these three trig functions with sign just parameterize a circle in R3. Now, my interest really comes from the fact not that S4 has constant curvature, but from the fact that since it has constant curvature, in particular, it's Einstein and self-dual, or I prefer it's both self-dual and anti-self-dual. What that means is that if you just restrict to one of these bundles of two forms, lambda 2 minus or lambda 2 plus, those bundles have constant curvature. The curvature tensor of those bundles is just the induced curvature tensor from the Levi-Civita connection is just invariant. So that's the thing I want to sort of develop, but in this cohomogeneity 1 context. Okay, so I'm going to fix the bundle of this is my usual convention, it's fix the bundle of anti-self-dual two forms. The reason for preferring anti-self-dual is that if you're doing this for CP2, you have to really use, if you want nice invariant curvature, CP2 is a self-dual manifold, so the nice curvature occurs on lambda 2 minus. But for S4 it doesn't matter. But anyway, given the orthonormal basis which I defined before, I can easily write down a basis because these forms on the right-hand side are orthonormal here. So I can just combine them in the usual way, 1, 2, minus 3, 4, 1, 3, minus 4, 2, and so on, to get a basis of the anti-self-dual two forms. And that's what I've done here. Be careful, there's no summation here. It's just sort of neat notation for cyclic permutation. So I have a basis, an orthonormal basis of anti-self-dual two forms, each of which has that form. Remember, the S's are functions of t involving, they're just sine functions with the shiftings. How do we know that this is forget the constant curvature. How do we know that this bundle here has constant curvature? Well, it's just, applying the Cartan formula, whatever. You know that, we've got a connection here, so nabla of omega, that defines d of omega k, and there will be connection 1 forms. And you've got to make sure that the curvature of those 1 forms is invariant. And one way of saying that is that when you work out the curvature of these 1 form, the corresponding curvature of this connection on lambda 2 minus, you get some constant times, you get the identity, which means that this object here has to be a constant times omega k. So you can solve this, and you find the solution is that the 1 forms are given by this simple expression. Here I need the cosine functions, because I've differentiated, and it turns out the curvature with my convention here is 2. This is all elementary because we knew that this bundle, is constant curvature. But on the other hand, understanding self-duality in this way was essential really for understanding G2 metrics on lambda 2 minus. So one needed really to fully understand all these equations for self-duality to understand, to prove that you can define metrics, well, 3 forms and 4 forms that are both closed on the total space of this vector bundle. So I make no apology for sort of presenting this. Now, you can try and solve in general this system of equations. You can do it quite easily for CP2, which is also self-dual. But if you want to prove this sort of system here and get the constant curvature, it's a very tricky business. I think it was done probably by Paul Todd and used by Hitchin. It's somewhat easier to do the hyper-Kähler case, in which you just want d omega k to be 0. And that's explained in this book by Thier and Hitchin on monopoles. And typically what you do to solve these equations is you don't leave the metric in the form dt squared. You make a conformal change, so you change the parameterizing the orbits by using the functions, which, whatever they are, and you make a change like that. This is for the hyperkähler case, but you do a similar sort of change to understand the self-dual non-zero scalar curvature case. Again, that's just sort of background. Now I'm coming on to talk about weak holonomy, and I realize I haven't really defined weak holonomy in this talk, but perhaps I need to say a bit about it. So in this talk, I'm only going to talk about two types of manifolds that have weak holonomy. The first class are the so-called nearly Kähler six-dimensional manifolds. So nearly Kähler, it really means weak holonomy SU3. And nearly Kähler, it's a misnomer, it's really nearly Calabi-Yau, because a nearly Kähler manifold, if you look at its curvature, it's identical to that of a Calabi-Yau manifold, except you've added on a term which corresponds to the constant curvature of the six-sphere. So when you look at differential system, exterior differential systems, and so on, the case of Calabi-Yau, holonomy SU3, is almost identical to the case of nearly Kähler. I think the definition of a nearly Kähler six manifold in terms of sort of the Levi-Civita connection is that nabla, I hope this is right, nabla xj, that J is the almost complex structure which will be non-integrable in the nearly Kähler case, applied to x is 0. I think that's true for all vector fields x. I hope that's true. And that will tell you that the intrinsic torsion is essentially totally skewed. So there's just the intrinsic torsion is invariant under SU3. That's one way of characterizing weak holonomy SU3. Another way is that there's holonomy SU3 means that there are parallel spinors. Weak holonomy means that there are killing spinors. But I won't really say more than that. And then there will be 7 manifolds that have weak holonomy G2, but let me just read through this. So I'm starting with an Einstein self-dual metric with positive scalar curvature, and even the case of the round metric on S4 is useful, but also CP2 has such a metric, and we'll mention others shortly. But the only complete examples, the only compact examples, I want positive scalar curvature of S4 and CP2. Then it's well known by now, that the bundle of anti-self-dual 2 forms has metrics, one parameter family metrics with holonomy G2, limiting to the cone. Okay, so here we have holonomy G2 coming from Einstein self-dual. If you look at the sphere bundle inside lambda 2 minus, that would be like the twistor space. I described that for S4. It's just CP3. For CP2, it would be the flag manifold. That twistor space has both a Kähler-Einstein metric and a nearly Kähler metric. Strictly means not itself Kähler. Of course, that would be true on a Kähler manifold because nabla j is 0, but I'm assuming that nabla j is not 0. So you can rescale along the fiber and you get this second Einstein metric, which happens to be nearly Kähler on the twistor space. And then you can go up one dimension by looking at the corresponding principal bundle associated to lambda 2 minus. And that will have at least 2 Einstein metrics, namely a 3-Sassakian one. Apologies, I didn't write down 3-Sassakian, but 3-Sassakian means that the cone over that 7 manifold has holonomy SP2, it's hyperkähler. And there's another metric, again by rescaling on the fiber, that has, whose cone has holonomy typically equal to spin 7. But both of these metrics would be called nearly parallel G2 or weak holonomy G2. And again, I'll write down equations later on. So those are that's the weak holonomy in the title of my talk. So I'm just special types of 6 manifolds, nearly Kähler ones, and special types of 7 manifolds nearly parallel G2. I mean, weak, again, is a misnomer, because it's probably much harder to find these than it is to find metrics with holonomy, SU3 or G2. And in fact, Gray introduced a theory of weak holonomy involving subspaces, so that there are other definitions underlying this, but nowadays one just uses the terminology, I think, to talk about nearly parallel. Intrinsic torsion, in both cases, the intrinsic torsion is invariant. It's just an invariant quantity. And the key thing about the third case, we've gone up now to 7 dimensions. We've gone from 4 dimensions up to 7 dimensions, compact fiber now. And the interesting thing is that even if M4 is an orbifold, you can get examples in which these principal bundles will be smooth. And that was well known, I think, to Galiski and Boyer when they studied 3 Sasakin manifolds. So perhaps I should have put the stuff in at the bottom first of all. I mean, so nearly Kähler, which I've defined, another way of saying it is that if you have a nearly Kähler 6 manifold, then it's cone. This is a mistake here. There's a t squared missing. I meant to say the conical metric. dt squared plus t squared g has holonomy subgroup or equal to G2, whereas the sine cone, it's something I learned from Bobby, the sine cone on nearly Kähler is a nearly parallel manifold. But this will have 2 singularities. And another fact I sort of mentioned here is I sort of learned this, I think, from Misha, is that if you have a nearly Kähler manifold, a strict nearly Kähler manifold, so the Nienhuis tensor is non-zero, you can essentially recover the metric from the Nienhuis tensor. I talked to him at the cocktails on Monday, and our understanding is basically you just take the square of the Nienhuis tensor, and that produces a 1-1 form, at least at each point, and that will be proportional to the metric at each point. There may be a problem with S6 because of conformality, I'm not sure. But anyway, basically the structure of a nearly Kähler manifold is just determined by its non-integrable, almost complex structure. That was in a paper by Misha Verbitsky on nearly Kähler manifolds. Any questions? Very quickly, here's now the third example, slightly more sophisticated now, of my residual moment map technique. So in this example, again, I'm starting with CP3. Again, I'm taking, before it was SP2, but that's just double covers SO5. It's really SO5 that's acting on CP3, effectively, not SP2. I take its nearly Kähler metric, which it has, as the twistor space of S4 from the previous slide. And the subgroup of SO5 I want to fix this time is U2, but thought of as not related to the twistor space, but the U2 that's naturally inside SP2, the complex matrices inside quaternionic matrices. And then I'm also going to take the cone over CP3 because I'm interested in the conical metric with holonomy G2. And I'm going to, that therefore is embedded inside SU4. Again, before we had CP3 embedded as an adjoint orbit in SU4 with the standard moment map, which is written below. I'm scaling it with R+, that won't damage anything. And I get this map. I'm not projecting to M now, I'm projecting to some other subspace of SU4. And if I do it the right way, I'll get R3 plus R3. And in fact, what I'm doing is R3 plus R3 is simply the subspace of SU4 over U1 that's invariant by the action of U1 contained in U2. So if I do that, this is the quotient that I worked on with Bobby and Robert to understand the induced geometry when you take this quotient. So basically we're saying that this cone over U1 can be represented by a pair of vectors in R3. So you're sort of converting this to undergraduate geometry. And in fact, you're really using the Gibbons-Hawking, using a couple of Gibbons-Hawking maps, which are themselves sort of moment maps for hyperkähler structures. But in this situation, you don't really have a hyperkähler structure because we've muddled up the quaternionic. We're not taking the standard quaternionic structure I mentioned before. But using this sort of moment map technique, you can understand, really, I think it's just an interpretation of what we did. Okay, now when you do this, you get an induced by general techniques. You have a G2 metric, you take its quotient by U1, and this was motivated again by work of Haskins, Nordstrom, and Foscolo, in which they sort of constructed G2 metrics from on U1 bundles over Calabi-Yau. But here we just wanted to look at an explicit example of doing the quotient, and so you get an induced almost Kähler manifold, because you can scale the metric so that the induced 2 form is symplectic. So this is not really weak holonomy, it's a joke, and the weak holonomy is very weak, but the holonomy is very weak. In fact, the almost emission structure is extremely complicated. Recognizing what G is, identifying the 3 form is difficult. But there are some nice things one can say. So this is just from our paper that you can recognize quite quickly the symplectic form. This is really a digression in the lecture. Since this is a penultimate talk in the Simons meeting, this is you can recognize the induced symplectic form, find Dolbeault coordinates very easily in terms of these bivectors U and V. That's rather neat. And you can also identify the almost complex structure, and it has this, well, partly identified, it has this rather nice property that basically if you take one of these bivectors UV and you map it to U cross V, vector cross product, undergraduate style, assuming that's non-zero, the fiber, the inverse image, is actually a 4-dimensional J holomorphic surface, something which couldn't happen in a nearly Kähler manifold, incidentally. You can't have 4-dimensional J holomorphic surfaces, but in this setting you can. Okay, so that was a more complicated example of the sort of use of these moment maps. Now, the topic which is really at the heart of this lecture is to exploit these Hitchin orbifolds, which are also self-dual and Einstein. By the way, quaternion-Kähler is just another way of saying self-dual Einstein non-zero scalar curvature. Here, positive scalar curvature. In dimension 4. Yeah, I mean, it's the 4-dimensional version of what you would normally call quaternion-Kähler. And there's a quotient construction by Galiski and Lawson which sort of mirrors the hyperkähler quotient construction. So you can actually get these metrics from higher dimensions. I don't think that's possible for these Hitchin metrics, but anyway, the Hitchin's theorem is this, that I presented S4, constant curvature, CP2, I didn't give the details, but that has a self-dual, has a QK metric. These two are the first two in a family of orbifold metrics. Only the first one was smooth. They're all invariant by SO3, so cohomogeneity 1, 4-dimensional orbifolds. The orbifolds are homeomorphic to S4, but not diffeomorphic to S4, apart from the first one. And they're smooth everywhere, except remember S4, for this cohomogeneity 1 action, there were sort of two ends, two singular orbits, and they were both Veronese surfaces, RP2s. These metrics are smooth over one of them, say the left-hand one, but on the right-hand one, this right-hand RP2, there's an orbifold singularity corresponding to a cone angle, which is 2 pi over k. Okay, so that's you have this sort of local group, ZK, acting over this right-hand Veronese surfaces. A warning here, I'm using the convention, Ziller's convention, whereby the round metric corresponds to k is equal to 1, and the general one is 2 pi over k, whereas Hitchin actually has k plus 2. So just be careful if you study these. So in Hitchin's work, these arise as moduli space of monopoles on hyperbolic space of a given negative constant curvature that depends upon k and gets less and less as k increases. The first case, of course, apart from CP2, which is a global quotient, the first case of interest is k is equal to 3. And as k goes to infinity, these metrics approximate the celebrated hyper-Kähler metric of charge 2 monopoles in Euclidean space. And there are lots of motivations to the study. One involves you can convert the equations, which I mentioned earlier, into Pain-Lavey a second-order single differential equation, so-called Pain-Lavey sixth equation. And there are classical problems as well related to this as the background to this theorem. Okay? Now I'm going to get a bit technical, so I'll have to go quite quickly through this. But it's just to show the sort of thought processes involved. It's a bit difficult to follow the details, I admit. So first of all, forget the metric, forget Hitchin's metric, which I'm not going to show you these metrics. They can be very complicated. I think the simplest case, apart from CP2, is the case when k is equal to 4. The case k is equal to 3 is even more complicated. Ziller and company have written down these metrics in terms of algebraic functions. I'm not going to attempt to show you that. So just understand these metrics are very difficult to write down explicitly, but they can all, in theory, be written down explicitly in terms of algebraic functions. So in the cohomogeneity 1 sort of setting, one has to, basically, you have the two singular orbits, and you have to take disk bundles over them, or their normal bundles, and then glue these two things together so that you get the generic, the principal orbit. The principal orbits match from both sides. But to get this singularity on the right-hand side, you have to divide by zk. K here means zk, sorry. Z over k means over zk, so you do a bit of fiddling around for the definition here, and then you glue across the boundary of these disk bundles. And this symbol here means that the down arrow is because I'm embedding O2 into a lower block in SO3, G is SO3, and so on. And then there's an action by e to the minus, plus or minus 2it on the disk, because I want to make sure that the principal orbits are G over the Klein forgroup. Okay. So now let me explain what happens when k is equal to 3. And in that case, you can check the various actions of the isotropy subgroups of the singular orbits. I won't explain the details, but you need to look at both the left-hand side in which everything is smooth and the right-hand side in which we introduced this singular action by zk. You first of all understand how these isotropic groups act inside SO3. So if you like, how they act on R3, SO3 acting on R3. From that you can deduce, also from the formula, the gluing formula, you can deduce how these SO2s act on the tangent space to the 4 manifold at the singular orbit. So you'll have a sort of T along the singular orbit, the tangent space to the singular orbit, and you'll have the normal space to the orbit in the 4 manifold, which I'm calling O3 in this case. And they're the weights in the second row. And then we're only interested in, I'm interested here in lambda 2 plus, not lambda 2 minus, for reasons I'll explain. And then you can just multiply these weights in the second row to get the corresponding weights, to get the third row. So it's just 1 plus 2 is equal to 3, and 3 minus 2 is equal to 1. So what that means is on the left, somehow, if you're interested in lambda 2 plus, which I am now for reasons I'm going to explain, somehow the weights on the left are, or so-called slopes on the left are 1 and 3, and the slopes on the right are 3 and 1, and that's sort of symmetric, and then you can, what I'm really describing is the so-called group diagram to construct this total space, which is corresponding to lambda 2 plus. But I'm really interested in the corresponding principal bundle. And it turns out that these slopes, 1, 3, and 3, 1, are exactly the slopes that occur when you look at the cohomogeneity 1 action of SO4 on the Berger space. I know I'm rushing through this, but so this Berger space is SO5 over the principal SO3 that acts irreducibly. This cohomogeneity 1 action was first, I think, discussed by Podesta and Vediani. Again, the principal orbits are, as before, SO4 over delta, which I didn't really explain, but when I was looking at lambda 2 plus, I've now got an SO4 action. If I look at the principal bundle corresponding to lambda 2 plus, I've got the SO3 action on the base and the SO3 action on the fiber. So essentially, I've got an action by SO4. And you can work out, again, these slopes, and you find that they're identical to the slopes for this, for the principal bundle that corresponds to lambda 2 plus, P plus I'm going to call it. You'll get these symmetric slopes. In the Berger case, it's obviously a symmetric situation. You get exactly 1, 3, and 3, 1. Okay, so the conclusion, this is theorem of Grove, Wilking, and Ziller, is that in fact these two manifolds are equivalent. There's a Berger space, and the smooth, it's smooth. Using these weights, you can understand that the corresponding principal bundle corresponding to lambda 2 plus is smooth. You take its double cover because the Berger space is simply connected, and these are the same manifolds, you know, for the SO4 action. There's a slight problem in Ziller's papers. I think there's a bit of confusion between self-dual and anti-self-dual, but that's not essential. It's just terminology. So the Berger space happens to be, and this is their discovery, the principal SU2 bundle corresponding to self-dual two forms. And that's sort of, you can forget the next paragraph, that's just reminding you that B7 is a nearly parallel manifold. So nearly parallel, which I hadn't defined before, means that it's a bit like sort of G2. You have a G2 structure, so you have the 3 form and its Hodge dual defined by itself. But this time, rather than them both being closed, only star phi is closed because d phi is a constant times star phi, typically 4 times star phi. That's what nearly parallel means, or an equivalent definition, it's Kohn's holonomy contained in spin 7 or equal to spin 7, or you have one or more killing spinners. So it's well known that it's sort of obvious in a sense that SO5 over SO3, the Berger space, has this property. But you see, what I'm trying to say here is that I switched from minus to plus. First of all, I was talking about minus because I was saying if you take the anti-self-dual two forms, self-dual Einstein, then the corresponding SO3 bundle or SU2 bundle has these 3 Sassakin metrics and also another nearly parallel metric obtained by scaling the fiber. That would be on the minus side. This time we found, so that's true, so P minus of O3 has that property, but now we've found that the Berger space is P plus of O3, so that is also nearly Kähler. So you see both of these sort of SU2 bundles, SO3 bundles, are nearly Kähler. Now, I mean, in the work of Ziller and company, this is because they're interested in positive sectional curvature. And it turns out that it's now known that these manifolds P minus of OK are still candidates as 7 manifolds that might possibly admit metrics of positive strictly positive sectional curvature. And in fact, it's known that P minus of O3 does. There are at least 2 different metrics known with positive curvature. One, I think, by Grove and company, and Derricott also found, I think Ilka knows more about this than me, but also found a different metric obtained by modifying the standard the standard metric you would have on P minus. Okay. I should mention that Berger had this paper in which he produced two homogeneous spaces with strictly positive sectional curvature. One was the B7, which I'm calling the Berger space. There was a 13-dimensional one. There aren't many of these homogeneous. I think there's one example also known in dimension 24. There aren't many examples of these homogeneous, sort of exotic homogeneous manifolds with positive curvature. And I'm interested by this sort of Thorpe trick, which Ilke talked about, in which you can add artificially a four-form and try and get strongly positive curvature. And I noticed that B13 has at least one natural four-form. So, you know, maybe in years to come we'll be studying 13-dimensional manifolds. I don't know. Yes. Okay, what am I going to do? I think I'm going to go very quickly. It's running out of time. I'm going to go very quickly through the calculations that sort of I was trying to do. And in fact, there are lots of calculations underlying this. But I was trying to study with Raghini the homogeneous metric on the Berger space. And the first thing we did was found, again, this has been done by others. I think Gavin Ball in particular and Jesse Madnick understood this metric from the point of view as associatives they were studying. But we were more interested in getting an orthonormal basis for which you can write down the G2 structure. Okay, so here's the basis. So instead of using the sort of obvious SO3, we've got SO3 cross SO3, because SO4 is roughly SO3 cross SO3. Instead of using the obvious invariant one forms, we actually paired them by odd and even. You need to take these combinations of plus and minus of them. And then you can write down very neatly an orthonormal basis for which you can write down the 3-form and the 4-form defining the nearly parallel structure, the SO5 nearly parallel structure. And you notice there's a 0 here. So somehow this 2x2 matrix, and again, I'm using these trig functions. So this matrix comes in blocks of 2 because of the action of the Z3, the Waal group. So it's a very simple metric written in terms of these invariant one forms U and V. And then from that, you can also write down the metric if you want to. There it is, the metric B. And if you look at the form of that metric, you see how closely it resembles the round metric on S4, formally speaking, because of this term here. And in fact, you see this metric, this is really a conclusion, that this metric here, this invariant metric on the Berger space, you can think of it as arising from a sort of distribution on this fibration. This is not a smooth fibration, though. Because of this term here, you can think of this as sort of like coming from the base, but it doesn't because these are not invariant by the action of SO3. They're invariant by the diagonal action of SO3. So, but anyway, the idea is to try and identify and pin down this metric in the hope of generalizing it and finding new nearly parallel metrics. Sebastian Gotter actually proved that B7 is diffeomorphic to an S3 bundle over S4, but that's not relevant in this discussion because such a bundle can't be a principal bundle. And I think it was Bobby who asked me what the bundle was, and the answer is that up to sign, the Euler characteristic is 10, and the first Pontryagin number is 16. So it's not an obvious bundle. I'm going to skip this. I was looking at generalizing these metrics to try and see if we can get new nearly parallel examples. Can't do that, but you can get these nearly half-flat examples. 3 more slides very quickly. Here's another example. What is this? The fourth example of my sort of moment map business, will be well known to Robert. This time we're starting with a 5-quadric, which you can think of as a Hermitian symmetric space. It's an adjoint orbit inside SO7, the Lie algebra SO7. So I choose, obviously, what subgroup am I going to choose of SO7? Obviously, I choose G2. And Robert said in his lecture, he wrote down that he had this table that tells you that the quotient of G2 in SO7 is just the standard R7 representation of G2. And that gives you the map from which, so you project the adjoint orbit to R7, and you can say that explicitly by just taking an element of the quadric, which you can think of as a complex, Q5 sits inside CP6, which is in C7, so you can think of x and y as real vectors in R7. You take their octonion product, and that is the mapping which maps Q5 to a sphere inside R7. So that's the mapping from Q5 to S6, which Robert used in an early paper of his. You can think of this also as a submanifold of the sort of more standard twistor space in which there's no G2. This is G2 invariant, this map. You're really mapping to G2 over SU3, thinking of S6 as G2 over SU3. But you know, there are lots of applications of this mapping. What I wanted to do, I mean, this is well known, what I wanted to do is actually reduce from what was it before, SO7 to SO5, and therefore instead of taking a 5 quadric, take a 3 quadric. Just truncate the quadric, truncate my vectors, which were previously in R7, truncate them to belong to R4, but add on just a couple of coordinates. And if I do that, I can actually, again, applying the technique, but using the fact that rather than go to the quotient by SO4, the fact that SO4 is not simple gives more flexibility, and I can actually map to this quotient, which is really R7. And if I do that, there's the explicit formula. What happens is that SO4 is acting both on the 3 quadric and on the R7 in this sort of standard way that represents the inclusion of SO4 in G2. And the conclusion of all this is that you have an SO4 equivariant mapping from the quadric to S6, but the quadric itself double covers CP3, so you end up with an identification, well, a branched one-to-one mapping away from a two-sphere from CP3 to S6. S6 over Z2, I mean, I'm dividing out the Z2, I'm just dividing out the R4 by Z2. So the over Z2 here only affects the capital X and capital Y. So when I say S6 over Z2, I mean I'm dividing the R4 by Z2, but leaving the R3 alone. So I get this SO4 identification. So I'm really running out of time. This is the last slide. And this is related to things that have already been discussed here. It's related to taking S6 over Z2 and sort of replacing the Z2 singularities by Iguchi-Hansen spaces, except at a central, at the origin, and then trying to understand how you would resolve that, and could this be a local model for holonomy G2? And the fact that you have this identification that the sort of sphere becomes CP3 is very nice, but the problem is SO4 here is not a subgroup of SP2. So the sort of nearly Kähler metric on CP3 that's sort of suggestive of what I've been doing is, I mean, well, there's no other one, I guess, that's of cohomogeneity 1, but there's something not quite right. I'll finish there. Thank you.